Okay, so we are going to finish up chapter 13 today. And we left on starting to talk about synthesis. So, with this chapter, we learned a new way to form a new carbon-carbon bond. There's two routes we have learned so far, including this chapter. Why are you not working? There we go. One way was through a triple bond, a terminal triple bond. But that's going to give us an internal triple bond after, and we lose a lot of our selectivity. So with the Grignard, we don't. Now remember, our Grignard reagent, we don't have a lot of limitations with what the reagent is, except that we cannot have any acidic protons, we cannot have water, we cannot have anything that the Grignard is going to react as a base with instead of a nucleophile. So our Grignard is going to react with a carbon-oxygen double bond because it's electrophilic enough. Carbon that just has a leaving group is not electrophilic enough. We need a carbon-oxygen double bond. In the next chapter, we're going to learn one other thing that the Grignard will react with besides the carbon-oxygen double bond. But otherwise, the Grignard is just going to act as a base around anything else. If we have an aldehyde or a ketone, we get one addition because hydrogen and carbon are not good leaving groups. So we attack the carbonyl carbon, breaking the double bond and putting the electrons on the oxygen. The other thing that can happen is the Grignard can react with an ester because we have a decent leaving group in oxygen. Hydrogen, carbon cannot leave with a negative charge, but oxygen can leave okay. This can't react with carboxylic acid because the Grignard would just deprotonate the carboxylic acid instead of attacking the carbonyl carbon. In the case of an ester, we're going to get two additions because of that leaving group. In all cases, we form an alcohol. So if we want to take an aldehyde and convert it to a ketone, what we can do is react it with the Grignard, and then we can oxidize it back. Now we can't oxidize a tertiary alcohol, so we need to have, remember, one hydrogen present. So with our synthesis, if you see an aldehyde and then we form a ketone with a new R group, it's likely we're going through Grignard. So this is putting that all together, but I don't want it all drawn like this. I want to see our intermediate isolatable products, meaning I want to see these things drawn. Otherwise, I will remove points. I want to know that you know what each reagent does. So if we look at this example, we can actually do this reaction to form our product. Of course, always seeing if we have new carbon-carbon bonds. An easy thing to do is to find your starting material in your final product. And it's pretty clear that this branching is in our final product. So we see we added this new carbon-carbon bond. And we can do that through the Grignard. Our Grignard is going to react with our aldehyde. This already has a hydrogen. So that's going to form this product. And then we can oxidize that back. This is a number 1. To our C-double-bond-O. Now remember, when our Grignard attacks our C-double-bond-O, we do form the alcohol. And it doesn't really matter the oxidizing agent. We can use our chromic acid, or in this case, we can use PCC. PCC can react with a secondary alcohol to form our ketone. They both do the same thing. So in that case, that'll work. Remember, when your Grignard attacks, we must form the alcohol, because if we get this attack, we don't have a good leaving group, and we cannot have 5 bonds to carbon. It was a common mistake that I saw on the quiz. The water in the second step is where the hydrogen comes from on the alcohol, because we won't isolate our negatively bond oxygen. So let's look at this example. Again, the first thing we want to see is, do we have any new carbon-carbon bond? And the question is, how many carbons did we start with and how many did we finish with? So the answer to that is yes, we do have a new carbon-carbon bond. We're starting with 4 carbons, and we have 5 carbons in our final product. So we have this new bond. We do have a triple bond. We could deprotonate it and add a new carbon, but we would lose all selectivity through that route because our carbon-oxygen double bond is on carbon 4. So if we take our triple bond and react it with our very strong base to deprotonate it and our primary alkyl halide, what we're going to form is this. And if we reacted that with either of our reagents to add H2O, so BH3THF, or our mercury H2SO4, then we're going to form the same thing, which is we're going to get a mixture of products where our carbon-oxygen double bond is on 3 and 4, because we don't have a more or less substituted carbon. They're both substituted the same. Carbon 4 has one R group, carbon 3 has one R group. So we don't have any selectivity. So whatever reagent we use to add H2O to do our hydration, we're going to get a mixture of these two products, and they are not equal. So this is not a good route. We do not want this product, and we would get a 50% yield of it. So this is a bad route. But if we go through the Grignard, we don't have that problem. So if we go through a Grignard, our first step is, of course, we're going to have to make a carbon-oxygen double bond. So we can make a carbon-oxygen double bond by taking our triple bond. In this case, we do have our selectivity because carbon 4 is less substituted than carbon 3. So if we want the more substituted hydration, a less substituted hydration where our carbon-oxygen double bond is on carbon 4, then we can use our R2BH peroxide and sodium hydroxide. We could use that here, but we wouldn't get any selectivity. Once we have this, we can react to Grignard with. Now remember, we need a carbon-oxygen double bond for our Grignard to react with. So we can put in a CH3 MgBr, and that attacks our carbon 4. Forming our new carbon-carbon bond between carbon 4 and our new carbon 5. This leaves an alcohol, but we can easily oxidize that alcohol because it is secondary using our Na2Cr2O7, H2SO4, and H2O. So in this case, this route works a lot better than this bottom route, which does not work well at all, because we will get a mixture of products. So even though there's nothing inherently wrong with the bottom route as far as all of the reagents do work the way I say they do, my problem is I'm going to get a bad yield in the second route. I'm going to get a really low yield because I don't have any selectivity. Yes?
Could we use like a metal platinum or platinum HTPT
To do this stuff?
Oh, I have that.
Yeah, no. H2, platinum, palladium, and nickel will reduce this to this. But this is an oxidation here. So for the forward right now, I thought you meant in this step that would just reduce the triple bond all the way to the single bond and it won't have any reactivity. We could have made this our alkyl halide as well. That's another route. But first we need to reduce the double bond and put our bromine on the least substituted position. So we need to reduce our triple bond to a double bond, and then we could put a bromine and make this our Grignard and react it with a carbon oxygen double bond. That's also a route. But then your alcohol would be in the wrong position. So then you'd have to do more things. We're getting to the point where we have multiple possible steps, but there's better routes. So what I'm talking about is we could take this, we can reduce it, in this case we're not going to get sister trans because that's not going to be a cis trans double bond. So either reducing agent, not H2, platinum, palladium, or nickel, that would reduce it all the way to a single bond. So one of those two should work. Probably this one's a little bit cleaner and easier to use, but they both should work. Then we can make this our Grignard by putting our bromine on the least substituted position. So now this can attack, and we are adding a new carbon. But now if we react that with formaldehyde, notice now my alcohol is going to be on carbon 5. Because here we're attacking carbon 5, we're forming our new bond between 4 and 5, which we do have in our final product. That is true, we do have a new bond between 4 and 5. But the alcohol is on 5, so that means the alcohol is going to be on 5 in the product that's drawn from this. So, to get to our final product, we would then have to not oxidize. If we oxidize, we wouldn't have the product that we have. We have our carbon oxygen double bond in the wrong position. So we're going to have to make it a good leaving group. And then have an E2. Now that we have a double bond, we can do our hydration to get our alcohol in the most substituted position, and then we can oxidize. As you can see, this is a lot longer than the route that I previously showed. And also I'm running out of room. So this will put our alcohol on carbon 4, and then we can finally get to our final product by oxidizing this. Lab-wise and getting our good yield-wise, if we're comparing 1, 2, 3 steps with 1, 2, 3, 4, 5, 6, 7 steps, 3 steps, it's going to be a better route. So while there's nothing inherently wrong with any of the reagents I did, and we're going to get our major product as being the product we're showing in each step, this isn't the best efficient route. This might take you a month, this might take you 3 days. That's a huge difference with synthesis. And again, this one isn't as long, but our problem is it's only 2 steps, but we only can maximum get 50% yield because we don't have selectivity. So of the 3 routes I'm showing you, the best route is the first route, even though none of the routes are inherently wrong. And that's where you really get to in synthesis. Sometimes there will be multiple routes that both work equally well. This isn't the case. This is the best route that I'm showing you here on the screen. This is not the best route. So there will often be multiple ways you can do it, but better routes. Because again, you're trying to get the best and most amount of product. I don't know why it started there. Okay. Technically, I asked you this one last week. So for this question, the most efficient route is B. But A, B, and C will all work, actually. They'll all get you to your final product. But A and C both have really long routes that seem a bit unnecessary. So you should go through all of those and show how your final... You should go through all of those and for each step draw your intermediate products that are isolatable. And show that they all work, but our best route is our shortest route. That's going to give us our highest yield. So our most efficient route is B. A, B, and C will all lead to our final product with correct selectivity, but B is better. And if we look at this one I asked you last time as well. If you're given one like this and you want to know what the product is, take it one step at a time. Draw your intermediate products. Don't try to do this in your head. That's not necessary. That's how you're going to make mistakes. Draw your intermediate products for each step. So in our first step, we're adding excess MeMgBr. And we're reacting that with an ester. So we will get 2 additions with the loss of methanol. And then, of course, H3O plus is going to protonate the alcohol at the end. And we don't add it till second. So here's our original carbons. And we're going to get 2 additions of our methyl group. Plus our methanol, but that'll be removed. It has a low boiling point. It'll be removed in the first step where we're going to be isolating the product. Now this is a tertiary alcohol. That's what we see there. And we will get the 2 additions because we have an ester. Our next step is we're reacting it with tausyl chloride, and really they should have also included pyridine or some sort of base. That's going to make our alcohol a good leaving group. Then we're reacting it with NaOET in heat. That's our, remember, NaOET is a strong base, a strong nucleophile, but heat will promote E2. The fact that we have ethyl means that it's small, so we're going to get the most substituted double bond. This isn't new, we've learned all this, so you're just putting it all together. Oops, I added a carbon too many. 1, 2, 3, 4. Always number your carbons so you don't add a carbon too many. So we formed the most substituted double bond because we use the small, strong base. Then we're using BH3THF in water, followed by peroxide and sodium hydroxide. That's going to be our anti-hydration. We're going to get our anti-Markovnikov, so the least substituted, which is going to be on carbon 2. Our last step is PCC and CH2Cl2. That's going to give us our carbon-oxygen double bond. It's going to form a ketone because it's not an N group. It's a secondary alcohol. But PCC can be used for secondary alcohols. Its selectivity comes when we're using a primary alcohol. So that's where our difference in selectivity is. These that I drew, these are my this is my final product. These are my isolatable intermediate products. After each step, you're going to work up the reaction, remove byproducts, make sure your product is pure, do characterization, things like NMR and IR. That's what I want to see. This is how I want to see a synthesis look if you're drawing a synthesis. This is not a mechanism. I do not need to see curved arrows. Yes?
Could you combine steps 3 and 4 and just put a 1 and 2 and toss it?
I don't really want you to. You can, and the book does, but I want to know that you know what each step does. Because when I'm testing you, I'm testing you. There's a whole point of a test to make sure that you know what you're talking about. So if you're combining a bunch of steps, I don't know if you know what you're doing, especially when you give the wrong product. I don't know what your intermediate products were, so I want to see everything. Technically, you could draw it like this, 1, 2, 3, 4, 5, 6, 7. But in reality, you're going to isolate this compound before you take it forward, because you need to make sure that it's pure before you go to the next reaction. Just like if you're cooking with vegetables, you're probably going to wash them first, because if you don't, all that stuff is going to be in your food at the end. So when you're doing a reaction, you need to remove byproducts, otherwise they're going to be in your reaction the whole time. So that's why we show these intermediate steps. It looks a lot easier when you're drawing it on paper. This might take a year to do, depending on each reaction. So it looks easier when we're drawing it down with it. Drawing intermediate products allows me to see if you understand what's going on and also give more partial credit if you're on the right track. But I just want to see it because I am testing you. Oh, all my work moved. So the answer was for that one C, as we drew. So that's how you can work those and draw your intermediate products. You don't have to try to, in your head, do each step. So that's chapter 13. I did extend the homework until Wednesday because we hadn't yet finished it. Sorry about that. And I'll be putting up chapter 14's homework and bonus points this afternoon. So now we're going to talk about chapter 14. Chapter 14 has a kind of wider range of functional groups that we're going to be talking about. We have somewhat talked about each of these functional groups, and including epoxides throughout the chapters we've worked on so far. So we're going to be focusing on them, talking about why they're important, talking about their reactivity or lack of reactivity when it's important. So none of these are necessarily new, except for sulfides. We haven't really done too much with sulfides. But we've looked at other things. We'll talk about other routes to making epoxides. We're going to first start with ethers. The one thing with this particular chapter is we won't be seeing a lot of necessarily new reactions, but we will be learning a lot of new ways to name compounds. So we will be talking about a lot of new naming because we're going to look at naming all of these functional groups. So the first thing we're going to talk about is ethers. An ether is not an alcohol. An alcohol has an OH. An ether is a compound that has an oxygen that has two R groups attached. So that's our ether and OR. R groups can be alkyl, they can be aryl, they can be vinyl. They just have to be R groups. This is not an ether, this is an ester, because this is a oxygen right next to C double bond O. So that is not an ether, but as long as there's not a carbon-oxygen double bond here, then it's an ether. But that's a separate functional group and has completely different reactivity. Esters are pretty reactive, ethers are not reactive. And we're going to talk about ether reactivity. So you do need to know your difference between functional groups. So, of course, like I said, we're going to talk about naming. So what we do when we first look at functional groups, and then we're going to really dissect the functional group. So a couple of things about ethers. The way common names are used pretty often. So the common way to name ethers is naming each R group on each side of the oxygen and then putting ethers. And of course you're going to arrange them alphabetically. This is really useful for very small ethers and the most common naming for most small ethers. For example, this is ethyl methyl ether. We have an ethyl on one side of the oxygen, a methyl on the other. We put it in order alphabetically and put ether at the end. You do put spaces between, typically in IUPAC we wouldn't put spaces between ethyl and methyl, we do put spaces here. Another one, we have a tert-butyl on one side, we have a methyl on one side. Remember, tert is not alphabetized, so B comes before M. So tert-butyl methyl ether. And some of our most common are used as solvents like diethyl ether and dimethyl ether. Diethyl ether is the most common. So that's our common way, and for most simple ethers, that's how they're named, especially most ethers that are used as solvents. For more complicated ethers, the IUPAC naming system is used, and for that system, we choose a parent, our longest R group, and if we have other functional groups, this is the best route to name ethers as well, because our other functional groups will typically take priority. So either our R group is our longest parent, or our parent that contains all the other functional groups that we have in the compound. And then those other half of the ether, the OR part that's not part of the parent, is a substituent, and we call it an alkoxy. The alk being whatever number of carbons. So if it's one carbon, a methoxy. If it's two carbons, an ethoxy. If it's 12 carbons, actually I don't know what 12 is. I never really looked at 12. If it's 10 carbons, a dicoxy. There won't be often ones where you have 10 carbon as a side chain, but just in case. So that's just an alkoxy substituent. So our larger of the R groups are the parent chain, or the R groups that have the more substituents, the more functional groups, and then the smaller of the R groups is an alkoxy substituent. So for example, our parent chain would be the longer chain. We have 5 carbons there, so that's pentane parent. And then our substituent is the OR group. That's an ethyl, so it's an ethoxy substituent, and then you just put the locate number. In this case, there's no other functional group, so this would be 1. So 1 ethoxypentane. For any complex ethers, this is the best route. This particular ether could also be used in the common system, but I'm going to show some examples of more complex systems where this is the best route. If there's any other functional groups, chirality, things like that, this is a better route. And of course, we want our lowest numbering system possible for our substituents, or let's say we have an alcohol that takes precedence, so that would have the lowest numbering system. So let's look at an example. This one is way too complicated to name as the common naming system. It would be really hard to name as an alkyl-alkyl ether. because one side's pretty easy, but the other side's complicated. So in this one, it's much easier to find the parent chain and name our ether as a alkoxy substituent, because that's an ethyl group. We have two CH2 groups on the other side of our oxygen. So in this case, our parent, the best route would be the one that contains the carbon that's attached to the ether, contains our double bond, contains that chlorine. So we have some substituents, and we want our lowest numbering system possible for our double bond, because our double bond takes priority of all the things that are here. Of course, if we number from the right or the left, our double bond is 2. So since that's the case, then we'll just choose our lowest numbering system possible. So this is the best route, because if we number the other way, we're still going to have our double bond at 2, but then we're going to have a substituent at 2, 2, 3, and 4 versus 1, 2, and 3. So this route is a bit shorter. But we would typically put our double bond as having priority. Now remember, oxygen is not part of the parent chain. The parent chain is carbons. So do not number the oxygen and use that as your carbon name. So our parent name is butene. We do have that double bond. And we would locate that either 2-butene or butene, whichever route. That's both okay. This route would not still gives us our double bond at 2, but gives us a higher numbering system for all other substituents. So our substituents, we have our ethoxy, and that's on carbon 1. Then we have a methyl and a chloro. We're going to put this together alphabetically. C comes before E, E comes before N. So we have our 3-chloro, 1-ethoxy, 2-methyl butene. Now remember, this isn't an ethyl, it's an ethoxy when that's an ether. That is a substituent. And then, of course, we have a double bond that is E or Z. In this case, it's E, so we need to specify that. And that just goes at the front, just like any other. If we had any chirality or anything like that, it just goes to the front. We don't need a locate number because we only have one double bond. You can put it, but it's not necessary. We don't have any chirocenters in this particular example. So you're treating, when we have a more complicated ether, just as a substituent, and the substituent is the OR, and it's named based on the amount of carbons it has. Now remember, this isn't a propoxy. We're not counting the oxygen. We're just counting the amount of carbons. There's 2 carbons to a methoxy. If we're drawing this one, or 1-methoxy, cyclohexene 3-ol, clearly our parent is a 6-membered ring, cyclohexane, with a double bond and an alcohol. So there's my 6-membered ring with my double bond. And my alcohol is on 3. My methoxy, it's a meth, so we have a CH3. It's an OCH3 on 1. And I held up doing the alcohol because that's our R group. So that is R. You can double check that. And I could have started the double bond anywhere, but of course my numbering for the double bond starts on 1. So looking at this one is only giving us that common name route, and this particular one would be okay to name with a common name. So we have a isobutyl on one side, and this is a sec-butyl. Bless you. So in this case, we have, not isobutyl. We have our isopropyl and the sec-butyl. And remember, we do alphabetize iso. So it's B and then I and ether. This one can also be named based on the other naming system. If we were naming this one based on the other naming system, our parent would be our longest continuous chain. So that would be butane. And then our substituent would be isopropoxy. And of course, it's on 2. And I can't really number or tell you my stereocenter. I do have stereochemistry at 2, but I'm not getting geometry, so I can't label it as R and S because I don't know what's coming forward and what's going back. So it's just assumed that we have a mixture of R and S in this case. So my common name would be the sec-butyl isopropyl ether, but my IUPAC name would be the 2-isopropoxy butane. Fairly straightforward. I don't know why it does that. It drives me crazy. So let's talk about the ether. Our typical oxygen with 2 hydrogens has about 105 degree angle. Now when we look at our ether, we still have an oxygen, it's still sp3, just like both oxygens are with water, and our methanol. But of course our angle is a little bit bigger because we have a CH3 and a hydrogen. Hydrogen's still small, but my CH3 is taking up more room, so it pushes my angle a little bit bigger. Remember, these are bent because alcohol has 2 lone pairs, and the lone pairs take up more space. So the oxygen lone pairs push the 2 single bonded atoms closer together. But when we look at our ether group, we see a bigger angle because, of course, the R groups take up more room than a CH3 and a hydrogen. So we still have a bent structure, but these 2 things are repelling each other more because they're bigger. So that makes sense. But overall, they're still bent. We just have a bigger angle because the R groups have repulsion. The next thing we're going to talk about is boiling point. So with our alcohols, we have pretty relatively high boiling points because we have hydrogen bonding that can exist between 2 molecules of an alcohol. We have a partial positive hydrogen, a partial negative oxygen. With our ethers, however, they typically, depending on the size of the R group, very, very small R groups can form hydrogen bonds with water, but an ether cannot form a hydrogen bond with itself because it doesn't have the donor. It doesn't have the hydrogen that has a partial positive charge. So our ether has an acceptor. It has 2 acceptors. It has 2 lone pairs. So it can hydrogen bond with other things, but not with itself. Now remember, our ether has 2 R groups attached. So with our alcohols, we had water solubility up to about 4 carbons because we had both a hydrogen bond acceptor and 2 donors. But with our ether, we only have acceptors, and we have 2 R groups on each side of the oxygen that kind of blocks those acceptors a little bit. So as far as the amount of R groups, dimethyl ether is pretty soluble in water, but diethyl ether isn't soluble in water. We actually form 2 layers with diethyl ether. And oftentimes in the lab, you'll hear ether, and it's just assumed it's diethyl ether because dimethyl ether has such a low boiling point that it's really not very liquidy at room temperature. But our diethyl ether is really easy to work with at room temperature. So we don't have a lot of water solubility once we have larger ethers. So that explains our boiling point. Ethanol has a pretty high boiling point because it can hydrogen bond with other molecules of itself. But diethyl ether at room temperature is a gas, its boiling point is negative 25 degrees Celsius. Comparing that to propane, though, it's still higher. And remember, these are all pretty comparable because they all have roughly the same amount of atoms. So they're comparable. We don't have a lot of difference in London forces. So our propane is very low boiling point. Our dimethyl ether is still pretty low boiling point. Now, of course, the more carbons, the more London forces, so we can have a working boiling point, but dimethyl ether is still pretty low. We do have dipole-dipole interactions, however, but it's not as strong interactions as hydrogen bonding. Since we don't have hydrogen bonding, we have a lower boiling point than things like alcohol. So comparing the more R groups, the higher our boiling point gets. Diethyl ether's boiling point is only 35 degrees Celsius. Room temperature is around 27 degrees Celsius. But that's really useful for us. Diethyl ether is a really common solvent. We'll talk about it in more detail. But one of the uses is, besides the fact that it's polar, so it can solubilize a lot of organic compounds, its low boiling point means it's easy to evaporate. So it's really easy to remove it, and most of our organic compounds are going to have a much higher boiling point. Typically, they're solids at room temperature. So this can evaporate off, and we're left with our product. That's really nice. That's called a volatile solvent because it's easy to remove. Sometimes water as a solvent is difficult to remove. It's harder to evaporate water. Now, you know you can, if you have salt water and you boil it in a pot at home, you can boil off all the water and get the salt back. But most cases, a lot of our organic compounds might have boiling points closer to 100 degrees C. So it's not as useful with water. Diethyl ether is really useful being volatile. Dipropyl ether, however, is going to have a much higher boiling point because we have 1, 2, 3, 4, 5, 6 carbons. So we have more London forces. So that's a bit higher of a boiling point and not used as much as a solvent. Diethyl ether is used a lot. So of course we can see that. And again, this is nothing new. So ethers typically our most common use for small simple ethers is as a solvent. We have low boiling points, so they're easy to evaporate after the reaction is complete. We want to remove the solvent, isolate our compound. But they're dipolar, meaning that they can stabilize charged or partially charged transition states, which is usually what we want our solvent to do to help our reaction to lower our activation energy. So we need that polarity for that. Also, the other nice thing is that our ethers are not protic. So that's a really big advantage. We do not have a partial positive hydrogen, so we do not have any acidity. And that's important for some reactions we've been using. What would be a great reaction to use ether as a solvent that we've been talking about? Where an acidic proton would be a bad thing to have. Our Grignard. We cannot have an acidic proton in a Grignard. That means we can't use a Grignard with water present. We need a solvent because most reactions in organic chemistry, most reactions in chemistry are done in the liquid state. But most of our compounds are solid at room temperature, so we need to dissolve them. Because we don't have a lot of molecular movement in the solid state. Now there's a couple of reactions that are solid state reactions, but not very many. We want that molecular movement. Our molecules have to bump into each other to react in the right position, in the right shape. So being in the liquid state is important. So what we do is use solvent. But we can't use a solvent that has an acidic hydrogen for a Grignard. So an alcohol is out. We need something that's going to be polar, because remember our Grignard has that very big negative charge on the R group. So we do want something that can help stabilize that. But we don't want it to react with our Grignard reagent. So ethers are used. Specifically, like I said, diethyl ether is the most cases. That can be dependent for what your R group looks like, but diethyl ether usually works really well. So also in hydride reagents, you sometimes can't have water present, like lithium aluminum hydride, so ether is a good choice. So looking at these, if we're ranking them from lowest boiling point to highest boiling point, of course 2 is going to have the lowest boiling point. We don't have any polarity. And these are all have roughly the same amount of London forces, so they're all pretty comparable. Then we have 5, which has no capability of hydrogen bonding. It's our ether in this case. This is our diethyl ether. We have an ethyl on each side. And then 4, between 4 and 3, those both have 1 alcohol, but 3 only has an alcohol in our groups. 4 has an alcohol and an ether, so that gives us more capability of hydrogen bond acceptors. So 3 is slightly lower boiling point than 4. And then 1, of course, has the most hydrogen bonding capability, so 1 would be the highest boiling point. So this is not new, we've been doing this since last semester. So this is how our diethyl ether can help stabilize our Grignard reagent. It can help stabilize the positive charge on the magnesium, which means that allows our Grignard reagent to be even more reactive, and it helps solubilize all of our compounds. So this can be really useful for our Grignard. Now there are other times when we can use specialized ethers to help in solubilization. So our interaction between ethers that have lone pairs and metal ions, or stronger for compounds that have multiple ether oxygens. So we call those polyethers. So a scientist decided to try to come up with a way to make even better ether-containing compounds for solubilization and also reactivity. Not of the ether, of the reaction that we're talking about. So what he looked into was making cyclic ether compounds to help solubilize certain metals. And we're going to talk about why some of these are really important in reactions. So he called them crown ethers because they look like crowns. And the size that he found worked the best, or the ether linkage that he found worked the best, was an ethyl group. So all of these have 2 carbons in between oxygens. So what we have is the most common that he found to work. Now he didn't just prepare 3, he worked with a bunch of them. This is his main results. Was he found 12 crown 4, 15 crown 5, and 18 crown 6 worked the best, depending on which metals he was using. And the metals that he specifically looked at were some of the counter ions that we've seen, and we've kind of talked about but often dismissed, because we said, well, they're counter ions and they're not participating in the reaction. And that's true for the most part, but our counter ions can affect our reactivity. So first we're going to talk about the naming system for these, which you will need to know how to do, but it's super easy. So the naming system is pretty easy. The first number, in this case 18 crown 6, the first number 18 is the total amount of atoms in the ring. So that's carbons plus oxygens. Now not hydrogens, because hydrogens are not bounded together to form the ring. They're just part of the carbon. So talking about the atoms actually forming the ring. So what we have here is 18 talks about all of those atoms. And the way these work is our crown structures, all of our oxygens face in, and our carbons face out. They have that partial negative charge. So basically what we're doing is, remember how we talked about soap in chapter 1, and how soap can solubilize things by the polar heads facing out and the nonpolar tails facing in, forming a micelle, and they can have dirt go in the middle and be cellulose. It's basically the same concept, where our polar part, our oxygens point in, and our nonpolar part, our carbons face out. So our metal, our counter ion, which is a metal, in this case potassium, interacts with the oxygens in the middle, and that allows it to be solubilized in nonpolar solvents. Because remember, potassium, if it has a positive charge, it's not going to solubilize very well in a nonpolar solvent because it has a positive charge. And if potassium isn't dissolving in our solvent, it is holding really tight to our fluorine. If it's holding really tight to our fluorine cannot act as a nucleophile or whatever we're trying to use it as. So essentially our counterions are important. If they're held too tightly to whatever we're trying to use, then that thing we're trying to use isn't going to be reactive. So what this does is allow it to be dissolved really easily in a nonpolar solvent. So as far as the naming, like I said, the first 18 is all the atoms in the ring, oxygens and carbons total. And then this Y, the 6, is the amount of oxygens. So what we see is 18 crown 6 has (18) total atoms, and then 6 oxygens. And then the crown's just in the middle. Now 18 crown 6 works best with fluorine. Our other ethers work well with our other metals. So 12 crown 4, being our smallest crown ether, interacts the best with our smallest counterion, lithium. 15 crown 5, which is our middle ether, works the best with sodium, which is our middle counterion. And then 18 crown 6, which is our biggest one that we're really going to talk about, works the best with our biggest common counterion that we use in organic chemistry. We don't usually go anything bigger than potassium, but we've also seen sodium and potassium the most. Lithium is also in that first row of the periodic table, so it's often a counterion as well. So depending on which counterion we have, that depends on which ether we will use. So know which ether solvates which metal. Again, the ether will go in the middle, and that's going to be our polar part, and then the nonpolar is going to be in the outside, so then we can solubilize these in a nonpolar solvent. Why is that important? Well, normally our metal ions aren't soluble in low polarity solvents because we don't have enough partial charge to solubilize them. But if we were trying to do a reaction with a low polarity organic solvent, because let's say our organic molecule didn't have a lot of polarity, we can use these to make the reaction happen because it'll solubilize our counterion this way. An example would be if we were trying to use KF. We don't use fluorine a lot because usually fluorine binds too strongly to its counterion. And we don't usually have a lot of solubility because F negative is so electronegative. So because of that, we don't get to use fluorine very much. But if we wanted to use fluorine, we can use a crown ether, which will solubilize KF, whereas most things don't, usually in our nonpolar solvents. And then we can use it to do, let's say, a substitution reaction, which we haven't really used a lot of fluorine in substitution reactions because of this solubility issue. This thing is pretty nonpolar. We have this little bit of polarity here, but it's pretty nonpolar, so it won't solubilize in a solvent like water. That wouldn't solubilize it. We need a solvent that's pretty nonpolar. That means KF would not dissolve. So we can use 18 crown 6. That'll dissolve our potassium and allow our fluorine to attack in a substitution-like reaction. So this is just your review. Know the differences. So that's our ethers, and then we're going to talk about how to make ethers on Wednesday. Going backwards. You can pick up your quizzes